So the idea is simple, right? And it's used in GR a lot, right? The idea is that you take a solution to Einstein's equations with a high degree of symmetry, right? That's either, the flat background when you're doing gravitational waves, or the FRW solution when you're doing cosmology, or, black hole solution when you're studying normal modes and stuff. And then, so that's a nonlinear solution to Einstein's equations, but the trade-off is that it has high symmetry, and then we perturb on top of that. So we add tiny perturbations on top of that, which are linear, but with less degree of symmetry, right? Or in particular, with no degree of symmetry. So in this case, right? So we're going to take the metric, and we're going to write it as the background solution. And the background solution, as we have seen, depends only on time, right? There's a scale factor dependence in here, but it's everything comes in a time, everything's just time dependent, and then we add on top of this tiny perturbations. Now those are going to depend on time and position, but the trick is that we're going to assume that they are tiny, right? The same thing we're going to do the same thing for the stress energy tensor. Splitting into a background stress energy tensor that depends on time, and then tiny fluctuations of the stress energy tensor that will depend on both time and space, right? Because of homogeneity and isotropy, right, all background quantities can only depend on time, while fluctuations on top of that depend on both time and space. And the reason why we do this split is that if we assume that these perturbations are tiny, then we can solve Einstein's equations. And so basically, we linearize Einstein's equations, which are typically hard to solve and nonlinear, right? So we linearize them, and we can actually solve them. Now, the same idea can be applied to the different areas, right? You have probably seen it. Gravitational waves, same thing on a flat background. Think about perturbation theory around black hole solutions or rotating black hole solutions and stuff. Now, there's one technicality. There's one technicality here that we basically said, okay, this thing is small, right? This perturbation is small. Okay, the problem is that we haven't really specified small with respect to what, right? So this is a formal problem in perturbation theory in GR in general. So we just invent typically a smallness parameter, and we say, okay, this is multiplied by some parameter which is small. But if you're interested in more formal things, this is one of the perturbation theory open problems, right? That we can't really define small. Why? Well, it boils down to the fact that the components of the metric have no physical meaning, right? You can easily change coordinate frame, right, and alter arbitrarily the entrances of the metric. Very good. So let's see what happens when we actually do this in practice. So let's write down the perturb metric for around FRW, right? So we are going to write ds squared equals a squared, and this is in conformal time. And then it's just a matter of writing down everything we can, right? Very good. So we have written down tiny perturbations of the FRW metric in conformal time. We are going to consider flat FRW solution because doing perturbation theory around a curved background is technically more complicated. Yes? Yeah, this is just a convention, right? So this is just a convention because these guys here will depend on both time and space. So we just factored out an a squared. Okay. But now you see A is natural for the background metric, right? Because it's the only thing you can have there because of the high degree of symmetry you have at the background. While these guys here are just random functions of time and space, so they can really be whatever. Okay. Very good. Um, okay, so now the next thing we want to do to build up our perturbation theory is to split these perturbations based on how they interact with homogeneity and isotropy, right, on the 3D space. Okay, so we ask ourselves, okay, whether these fluctuations here, which are in principle completely arbitrary, how do they interact with the fact that we have basically spatial indexes, right? So, and this is the idea of doing a scalar vector and tensor decomposition of perturbation. Okay, with respect to the three-dimensional metric. Okay, so we ask, this is a spatial perturbation. How this reacts, can we decompose it basically as 3D vectors, right? So A is already a scalar, so we are not going to do anything, right? While B, so B has an index, right? So we would like to write B as di B as the gradient of a scalar field, right? The 3D gradient of a scalar field plus a vector field, and this is the scalar part, and this is the vector part. Now, since I decompose basically using the gradient of the field, then by construction, di is equal to 0, okay? So the vector part has 0 divergence. And the same thing we can do with the perturbation to the spatial part of the metric, right? We can write it as 2c delta ij plus 2 di dj e, right? And this is the scalar part of the metric. Plus 2 di ej, and this is the vector component, plus 2 ij, and this is the tensor component. Okay, and as before, basically this decomposition allows us to say that the divergence of the vector component is 0, while for the tensor component we have 0 divergence and 0 trace. Okay, so this basically tells you why we wanted to build basically this split, okay, to isolate the degrees of freedom that we have. And this is the usual thing you would do, for example, in when doing gravitational waves, that you find that your tensor components, well, are traceless. Now, how many degrees of freedom we have? Well, typically, right, the metric is symmetric, right? 4 by 4 symmetric means we have 10 entrances that we need to specify. So let's count them, right? 1, 2, 3, 4, 5, well, 1, 2. These are, well, let's count the scalar. 1, 2, 3, and 4. So we have 4 scalar degrees of freedom. And then let's count the vectors, right? So we have two vector perturbations, 1 and 2. So naive counting would be 6, right? But we have two constraints, right, which remove 2, so we end up with 4. Then we have 4. And then tensor, well, the tensor component is here, right? So this is 3 by 3, so it means we have 6 entrances. But let's look at how many constraints we have. We have 1 constraint plus 3 constraints, so that's 6 minus 4, so it's 2. Okay, so we still end up with 10. We have conserved the freedom we have in specifying the metric. We have just decomposed it in a way that's useful. The reason why this is a useful decomposition, which I'm going to state, is that these degrees of freedom, so scalar vector and tensor fluctuations, in linear theory decouple. Okay, so we get different Einstein's equations for these 3 types of degrees of freedom, which, you know, is better quality of life. Okay, allows you to solve things easy, allows for easier solutions. Very good. So let's now play the same thing. Let's now play the same trick with the stress energy tensor. So we want to write down the perturbed okay, so same idea. T mu nu equals background T mu nu plus delta T mu nu. And now we want to write down this guy here explicitly. So let's start with T00. Well, this is minus background density plus delta rho, density fluctuations. Then Ti0, this is rho plus P Vi, right, where this is the velocity of the field. This is literally just perfect fluid, okay? We're just writing down explicitly perfect fluid, and we are basically using the fact we are plugging in this thing here in the perfect fluid stress energy tensor, noticing a few things, right? So for example, here I have something that's background, right? This is background density plus pressure that multiplies velocity, and this happens because velocity at the background is 0, right? You can't really have any velocity field at the background because homogeneity and isotropy holds. So if I want the linear term is going to have something evaluated at the background that multiplies a first order fluctuation, okay? Now this is also called, this whole thing is also called momentum density. And Vi is bulk velocity, is also referred to as bulk velocity. Then Tij is equal to pressure plus pressure fluctuations, delta Ij. So this is background pressure, pressure fluctuations. Now, this is the trace part of the stress energy tensor, right? And then we are going to write these fluctuations as pi ij. Now, this tensor here is called an isotropic stress tensor. Okay? And since this is the trace part, this has to be traceless. Okay? Now, again, you could calculate these quantities from first principles, from a distribution function. That's a story for another time. But in principle, you don't have to assume something for these if you don't want to. Very good. Now, the scalar vector tensor decomposition here works slightly differently, right? We have few fluctuations that are already scalars, right? Pressure and density fluctuations are already scalars. And then what we're going to do, we're going to take the vector here and decompose it, well, the vector here and decompose it in a scalar component. Well, this is divergentless. And then we're going to take the tensor component here, well, the spatial component, the spatial fluctuation components here, and break it down again as a scalar part plus vector plus tensor part, okay? Now again, when I call these vectors and tensors, these are not, clearly these are not vector and tensors in 4D space, right? These are vector and tensors on the 3D maximally symmetric foils, okay? So I have to say this is the divergence of this guy vanishes, and this guy here okay, so this has to hold for both. Very good. Now, this is a lot of notation, right? But it already allows us to, to see something that's quite interesting, right? The first thing we can notice is that, so given that scalar vector and tensor fluctuations decouple, right, at linear order, this already tells you that basically tensor fluctuations here in the metric can only be sourced by tensor fluctuations in the stress energy tensor, and tensor fluctuations are due to anisotropic stresses, okay? Which means there's not going to be any cosmological gravitational wave if you have perfect fluids, for example, right? So in a perfect fluid, this guy here vanishes, right? Because you only have density and fluid flow terms. So this quantifies imperfections in the fluid. That's the only thing that's going to generate or absorb gravitational waves. Okay. So it is a lot of work, but it allows you to show something fun immediately. Now, there is a problem where when we do this type of decomposition, and the problem is how do we cope with coordinate transformations? Okay, so this is the problem of gauge freedom. Sorry. Which you have already encountered when discussing gravitational waves. Now, with gravitational waves, you enjoy the fact that the background metric is, has the largest degrees of symmetries possible, right? It's flat. It's fully flat, right? So you could get away with a discussion of gauge freedom in a way that was quite easy. That becomes slightly more complicated in cosmology because we have less degrees of freedom at the background, which means we have to understand how coordinate transformations play with our split of metric fluctuations and stress energy tensor fluctuations. Now, this is a problem because clearly physics shouldn't depend on your coordinates. So that's that. So let's do a first example. So the best way to understand gauge transformations, um, I think is the following, right? So let's take as an example this coordinate transformation. So we take spatial coordinates, right? And we transform to some other reference frame by some function, right? Clearly, I can always do this, okay? I am just changing my spatial coordinates in a way that's time and position dependent. Very easy coordinate transformation. Now let's see how the metric changes. So the xi is the x tilde I minus d tau delta tau minus dk zeta I dxk. Okay. Now clearly this holds at first order. Now and so let's do this coordinate transformation, but let's do this coordinate transformation on the unperturbed metric. Okay. So we do this. So we start with FRW, right, and we do this coordinate transformation. What happens to the metric? Well, we have our usual a squared. Then we haven't changed time, right? So we get our usual d tau squared. But then I start having these guys here, right? So I have plus 2 d tau Okay, so as you see here, our seemingly harmless coordinate transformation, right, has transformed our background metric in a perturbed metric, okay, which now has spatial fluctuations. So we have induced, by changing coordinates, we have induced spatial perturbations, okay? So that's pretty bad. Let's do another example, and this example is I mean, it's going to be relevant for the discussion we're going to have on the last day, because it's at the basis of how we do dark energy modeling nowadays. So now let's do the same trick, but instead of transforming spatial coordinates, let's transform time. So we take tau and we send tau plus some function that depends on time and space. This works very badly. Okay. So this is a change in my time slicing, okay? Now let's see what happens to density. Right, so density, at the background level, density just depends on time, right? But I plug this in here, okay? I expand this to linear order, I assume this is small. So what I get is the same background density plus rho dot psi 0, okay? Now, as you see here, I've changed my time coordinate, and starting from an homogeneous isotropic density field, I now have something that has fluctuations in density, right? What's the physical idea here is that you basically have your constant time hypersurfaces, right? And you're introducing density fluctuations because at each point you are looking at a different time, right? And then since density evolves, you look at different times. There you have it. You have sourced density fluctuations, okay? Now, what's the problem? Clearly here we have done the exercise generating the fluctuations, but you can also go the other way around, and this is the problem for perturbation theory, because you can start with your perturb metric and perturb stress energy tensor, and then do coordinate transformations to erase fluctuations, okay? Very good. So let's see how we can cope with this. So let's define our general coordinate transformation as x tilde mu equals x mu plus psi mu of tau and x, okay? And then a little bit of notation. This is a 4 vector. So as you know, we are going to split it into 2 scalars and 1 3D vector components. So psi naught, we're going to call this t, and then psi I, we are going to break it down as this, a scalar component plus a vector component, okay, where we split this coordinate transformation according to basically scalar vector and tensors. And now what we can do is ask, well, how does the metric change when we do such transformation? Okay, so well, we start, you know, transform G mu nu is dx alpha dx mu dx beta dx nu G alpha beta, okay? Now we can take this relationship, assume that this coordinate transformation is again small, so linearize in this coordinate transformation. Why? Because we only care whether we are generating or erasing linear fluctuations, okay? And then what we can show is that the metric fluctuations we have defined before transformed in the following way. So A goes in A minus T prime. This is derivative with respect to conformal time minus H T. B goes in B plus T minus L prime. C goes in C minus HT. And this is a somewhat boring calculation. Again, I do suggest you do that once in your life if you're interested in these type of things, but it's not particularly. So this is the scalar sector. Then the vector sector transforms in this way. Bi goes in Bi minus L prime I. Ei goes in Ei minus Li. And then the tensor part is invariant. Okay? So that's one of, this is a technical calculation. This is one of the nice results, right? So tensor fluctuations are invariant of your reference frame in linear theory. Why? Because we are sourced by a vector, right? So here we are sourcing our coordinate transformation with a vector. So you can't really, that vector can't really change your tensor fluctuations. Now the same applies when we do this exercise. The same happens for clearly for perturbations in the stress energy tensor. Sorry. My cough is getting worse and choke doesn't help. So yes? Yeah? Only in linear theory. Only in linear theory. And you can imagine why, right? While so this is linear theory, so you can't alter the tensors because here you have only a vector, right? So and you can't multiply two of these because you're in linear theory, right? If you start going nonlinear, clearly you can take vectors and combine them in such a way that you get tensors, 3D tensors, okay? So the fact that this is gauge invariant is a result in linear theory. Okay. Very good. Any other question? Okay. So the stress energy tensor transforms in this way. Well, we basically change density fluctuations. Okay. And I'll save you the vector and tensor. The tensors again. The tensor part again is reference frame invariant. Okay. Now, the next problem we need to solve is that, okay, you see everything every fluctuation we have defined depends on the reference frame. Any fluctuation changes basically as we change the reference frame, which means we can't really attach any physical meaning to any of these fluctuations, right? So the next problem is how do we cope with this, right? So how do we cope with this gauge freedom, and how do we attach physical meaning to these fluctuations? Okay. So let me erase this. So as we have seen, there's basically two strategies. So the first strategy matches what we have done yesterday, right? Where basically at the background level, we had rescaling invariance, we had rescaling symmetry, right? So we had to cope with the fact that we could rescale the entire background, and we better get the same quantities. So the first strategy to fix these problems is to fully fix the reference frame. Okay. So basically, you fully fix the reference frame, then you specify what that reference frame is. You make sure you have no residual gauge freedom, okay, so that you can't do any specific different type of coordinate transformation and still change your fluctuations. And this is basically the strategy that people use the most. Why? Because this allows you to fix the reference frame to the one you need when you do your calculations, okay, to the one that's most convenient, okay. So for example, sorry. So for example, we'll see some perturbation theory calculations. Analytical calculations appear very well when done in a specific reference frame, while numerical calculations are much easier when you do them in a different reference frame, okay? So this first strategy is basically what everybody uses because it allows you to specify your reference frame to your needs, okay? And then once you've found the solutions that you're interested in, then you know how to change from one reference frame to the other. Now, the second strategy instead requires looking at gauge invariant variables, which means that we take these transformations and we define combination of these metric quantities that won't depend on our reference frame, okay? Now, clearly, you see that the same quantities enter there many different transformations. So you imagine that you build, mix and match these type of fluctuations to basically kill all the terms, okay? Now, this second strategy is useful because in here it's easier to attach physical meaning to your fluctuations, okay? So let's have some examples. I'm going to define gravitational potential fluctuations psi equals to A plus H B minus E prime plus B minus E prime, right? And then it's a simple exercise to just plug those coordinate transformations in here to show that this won't change when you change your coordinate frame, okay? At the same time, I can also define a different gravitational potential that mixes and matches my okay? And then the last thing I'll need is this rho delta, which is my gauge invariant density fluctuation. Okay, and you can easily verify that these won't change when you do these types of transformations. Very good. Now, clearly, in here, one of the interesting things here is that we have built a gauge invariant density fluctuation using the metric, right? So in here you see that basically we can mix and match, that basically the geometry enters everywhere, so we mix and match metric fluctuations with density fluctuations, right? And this is again, the idea that basically doing coordinate transformations would alter the geometry, but it would also alter the way in which you think about your density and velocity fields. Okay? Very good. So the strategy we will follow, okay, in the following, um, is that we'll take a hybrid approach between these two. We are going to see some calculation at fixed reference frame, okay? And the next thing I'll say is specify a few useful reference frames. Um, and then we'll check that results are gauge invariant, okay? But some things are better defined when we think about gauge invariant variables, and it's not a chance that, that the two, that I call the two gravitational scalar potentials, phi and psi, in this way, okay? So we'll see about it in a little bit. Now, clearly you can also define different types of gauge invariant variables when you have multiple components, okay? Because, for example, when you have one component, velocity transforms in this way. But if you had two components, clearly v1 minus v2 is gauge invariant, okay? And this, goes into the basically our intuition that you can, measure velocity differences, and your actual velocity depends on the reference frame, but velocity difference doesn't. Okay. Very good. So let's take a 10 minutes break and restart at 10. So very good. So we have seen how we describe the perturbed universe, right? How we decompose metric fluctuations and and stress energy tensor fluctuations. We have seen problems with reference frame definitions, right? And how we cope with that. So now I want to give you a couple of choices that people make. So basically a few reference frames that are useful and that you'll see very often in literature. So the first reference frame that people use all the time and that we'll use basically for analytical calculations is the Newtonian gauge. Which basically is the reference frame in which my equations look Newtonian, okay, or metric fluctuations look Newtonian. And this happens when I fix B equal E equal 0, and then the scalar part of the metric becomes a squared minus 1 plus 2 psi. Okay, and you see basically this has killed off diagonal metric fluctuations, and we are only left with two scalar fluctuations, okay, which basically look like Newtonian perturbations, and these two coincide with those two gauge invariant variables, okay? This is also known as conformal Newtonian gauge or Poisson gauge. from time to time. Now we'll see that the equations of motions look great in this gauge. The problem is that this reference frame is unstable at large scales when you want to solve equations numerically, right? So in practice, these perturbation equations are typically solved, or the perturbation equations that we're going to see are typically solved numerically. It turns out that this reference frame is very bad for solving them numerically. So that's that. So for numerical calculations, people use this other reference frame, which is the synchronous comoving gauge. Now the idea here is that a synchronous reference frame means that time is not perturbed. Okay, so I have the s squared equals a squared minus d tau squared. Very good. Now the problem is that this is not a full gauge fixing, right? So basically you can convince yourself about that because some of those relationships over there involve derivatives, right? So fixing the gauge is actually a problem, may have problems with boundary conditions, okay, which is the case here, right? So especially if you want, we want to kill A, right? So we need to pick a suitable T, okay, but that suitable T, that's a differential equation, right? That needs a boundary condition, okay? So where does that boundary condition come from? Well, it comes from basically the second part, which is the comoving statement, okay? So we need boundary conditions for both T and L, right? Because we want to kill both fluctuations. So in that case, you can achieve that by saying that for some species Q is equal to 0. Okay? So this makes it a fully fixed gauge. Okay? Now typically the comoving part, the component that you decide to be comoving with is called dark matter. Okay? Because that's easier, right? That's typically easier when you do the calculations. Very good. So these two reference frames are the ones that are most used when discussing cosmological perturbation theory, one for analytical calculations, one for numerical calculations. And if you just browse the internet for cosmological perturbation theory, you'll see a landmark paper discussing perturbation theory in these two gauges, right? Very good. So before we start discussing the dynamics of fluctuations, right? And then in the next couple of days, we're going to see what this dynamics implies, okay, which is the interesting part. We still need to get one technical issue settled, and it's basically how Fourier space works, okay? So we need to understand how to take the Fourier transformations of these fluctuations. Okay? So now, when discussing Fourier transformations, we basically look for solutions of these equations, right? So we want a basis of function that are, you know, eigenvalues of the Laplacian. Okay, so we want basis functions for which this relationship holds, right? Why? Because you see we have spatial gradients, we don't like spatial gradients. Okay, as simple as that. So now this is one of the places where the absence of curvature matters the most, okay? Because clearly this is the 3D Laplacian, okay? So if you have curvature, that's gonna have connection terms, okay? So finding the eigenvalues of this is gonna be much harder, okay? Now in flat space, we know the solution for the basis function of our Fourier transform, right? That's solutions of these equations are all of the form, it's plane waves, so is exp ik times x, okay? And this is the solution when we have flatness. If we don't, much more complicated. And then, you know, these functions allow us to write our function of x as a of k q naught. Okay. Now, this is one of the places where we get to appreciate our scalar vector tensor decomposition, right? And the reason being that in this case, this is the Fourier transform of our basically of our derivatives, okay? So whenever we have scalar equations, the vector part of our scalar equations is always going to have gradients, right? And those gradients are going to play nicely with our Fourier transforms, okay? Now, again, in linear theory, this Fourier transformation is useful because different Fourier modes K's evolve independently, okay? So you don't really have mode mixing, so you can fix K and then solve for fluctuations at a given scale. In fact, you know, K as units of length to the -1, okay? So small k means large scales, large k means small scales. But then this also immediately tells you that doing Fourier transforms allows us to compare length scales, okay? And what's the natural length scale in our game? Well, you know, we have another length scale, which is Hubble, right? So Hubble, as we have seen, the Hubble rate h scales like time -1, okay? So, I mean, these are the same units, you know, in units of c equal 1. So we can compare these two, right? And say, well, some given wave number, which is smaller than h, this means that this wave number corresponds to scales that are larger than the Hubble scale. So in this case, we say this wave number is above the horizon, okay? Which is a slightly misnomer. Yesterday we have seen that conformal time is the true horizon, okay? But then, that basically stick. H is an approximation for the horizon, so we are just going to say that this is above the horizon. And then when k is greater than h, then this is below the horizon, and k equals to h is called horizon crossing. Very good. So the reason why this is useful is because different k modes are going to evolve independently, which means easy to solve, and we can immediately classify the behavior of our perturbation based on some simple heuristics. Okay, so now we are in a good position to discuss equations of motion, which is basically the goal, the goal for today. Okay, so we'll fix the gauge to be the Newtonian one because everything looks nicer. Okay. Um, the same exercise can be done in whatever gauge you prefer. Equations will look very different in different gauges. This type of calculation, there's no magic in it. It's just long and rather boring, but it is conceptually straightforward. Okay, if you're interested in these type of things, do that once in your life, and that's that. Okay, there's nothing special. It's just a matter of taking a whole bunch of derivatives. So I'm just gonna state the results, okay, because that's what we want to use. So we'll start with the continuity equation. Right, so this is grad mu t mu nu equals to 0. Expand everything. Remember here that you have two connections. Now the 0 component is gonna give us d delta rho d tau equals minus 3h delta rho plus delta p plus 3 phi prime rho plus p minus di qi. Okay, so this is the first fluid equation that we get for density fluctuations. Now, clearly, this will give you two equations when you do the exercise. It's going to give you the background equations and this equation. Okay, now let's look at the structure of this equation. Look at this guy here. This looks like something that's very familiar, right? So if you remove delta, this looks like the background equation. Okay, so this first term, it's telling you how density fluctuation change because of expansion. Okay, so this is dilution because of expansion, and this is this looks like the background part. Now, but with respect to the background equation, continuity equation, we have two extra terms. Now, what's this guy, right? So this guy is a change in the local expansion rate. Okay, This is the guy that we sourced when we did the trick with coordinate transformations, right? So this is the perturbation to the time component. So this is how density fluctuations respond to changes in local expansion rate. And now this is the easiest of the terms because this is the usual fluid dynamics term. Okay, this is just local fluid flow. Okay, this is what you get in every dynamic dynamical equations. These two terms are extra because of the expanding background. Now let's now look at the I component. Okay, this is going to tell us how momentum flows Okay, so this is what you get for the for the I component. Okay, so let's look at this first term. Okay, so this is rho plus p v. Okay, but we have seen remember at the background we have seen that momentum decays, right? Like 1 over a. So velocity decays like 1 over a. So momentum decays like a to the minus 4, which gives you this minus 4. Okay, so basically if you ignore everything else, you would get that q decays like 1 over a to the 4th, right? And that's because it's momentum. Then this guy here, what is this? Gradients of the gravitational potential. This is just the gravitational force term. Okay. So this is typical in gravitational fluid dynamics. Okay. Clearly velocity is sourced by gradients of the gravitational potential. Okay, and then these two last terms, these are pressure gradients. Okay, you have scalar pressure gradients, you have anisotropic stresses, but basically these are all pressure gradients. Okay, now you may find these equations around the recast in every possible way. Now, one of the interesting things to note, right, is that basically the same problem that we have at the background also reappears at the perturbation level. So at the background, we didn't have enough equations to actually solve for all fluid degrees of freedom. Okay, we had one equations, density and pressures, two things we wanted. The same thing happens at the perturbation level. Why? Well, because we have, delta rho, delta p, q, and pi. Okay, so we have four quantities, four scalar quantities that we want to solve for, and we have two equations. Okay, so we need to assume something about the fluid, right, in order to make progress and solve these equations. So what people usually do is assume closure relations of the form, for example, pi equals to 0 for a perfect fluid. We know that anisotropic stresses are 0 for a perfect fluid, so this helps. But then we still have the problem with pressure fluctuations. And then what people do is basically, as we have done at the background, tie pressure fluctuations to density fluctuations, right? And the proportionality constant is called the sound speed. So this is the adiabatic sound speed that basically relates pressure and density fluctuations. Now, one of the interesting things you can ask yourself is whether this definition is gauge invariant. Okay, the result is interesting. Not necessarily, right? Not necessarily. So when CS squared is equal to omega or something like that, right? That's a particular type of fluid. Okay. That's that. I mean, just perform a gauge transformation. Yes, exactly, right? So I am saying, I am relating two quantities here. I'm saying, okay, uh, this guy is proportional to this other guy, okay? Now, is this definition gauge invariant, right? Very good. Now, these are simplifying assumptions. In practice, for a generic fluid, we can't really do these assumptions. Those are not done in practice for many components. Basically, the upgrade on top of this discussion is that you would need to solve for the perturbed phase space distribution of your fluid, which is clearly very beyond the discussion we want to have these days. Okay. So as it happens at the background, studying perturbations in the distribution functions of your components would give you these things from first principles, from basically your phase space distribution. Very good. So now we are in a good position to discuss Einstein's equations, which I'm gonna start here. Okay, so Einstein's equations to linear order, conceptually straightforward. So the zero equation gives you the following in Newtonian gauge. Now, so this is the 0, 0 equation, and you see this looks like the Poisson equation, right? This looks like the Poisson equation, well, in a given regime, right? So here, when spatial gradients are bigger than time derivatives, okay, this would look like the Poisson equation. So in Fourier space, this becomes k squared phi plus 3h okay. Well, with the minus, because we have k squared, right? So you see why it's useful to go to Fourier space, because now we can compare this guy here to this guy here and say that on scales that are below the horizon, okay? They are well below the horizon. This guy survives, this guy survives, and then this looks like the standard weak gravity Poisson equation, okay? Very good. So the zero I equation reads something like this. Not particularly insightful. Just notice one thing. This term here looks suspiciously similar to this term here, and we'll see why that's relevant at some point. The ij equation, right? We can split these equation into a trace equation and a traceless equation, depending on what they couple to. Now, it's not particularly insightful. So so I'm not entirely sure I want to actually write it. So the interesting part, so this is the trace equation, and it's complicated. Now the interesting equation is the traceless one, so the off-diagonal one, which tells you that phi minus psi is equal to 8 pi g a squared sum m pi m. Now, why this is interesting? Because this is telling you that the difference between the two the gravitational potential is sourced by anisotropic stresses. Okay. And we know that anisotropic stresses are very special because, for example, perfect fluids don't have them, right? So if we had a dynamical model where we only had perfect fluids, then this would vanish, and then the two gravitational potentials would be equal to each other, okay? Very good. Now let's go back and try to see what these equations become when we want to write them down in terms of gauge invariant variables, okay? So the idea is we know we have a list of gauge invariant variables. We have our equations of motion. We want to find equations of motion for our gauge invariant variables. Now I'm just going to do an example, which is the real Poisson equation, okay, which rests on the fact that that guy over there looks very similar to to part of that equation, okay. So I'm going to take that equation and plug it into the 0, 0 Einstein equation, okay? And this tells you that grad phi is equal to 4 pi g a squared sum over m delta rho m. Now I'm going to specify that this is in Newtonian gauge with the caption n plus 3h q at the Newtonian gauge. Now, and it turns out this is our definition of gauge invariant density fluctuations. Okay, so this is what we have called rho delta. Okay, so this equation here becomes grad square phi equals 4 pi g a square sum over m rho delta for our species m. And now each of these quantity is gauge invariant. Okay, the physical meaning of this guy here is that it's rest frame density, right? Because if I do a coordinate transformation where this goes away, I only have density fluctuations, right? So in the reference frame where I have no velocity, this equals this, which means the physical meaning of this quantity is rest frame density fluctuations. And this is tied to the second derivative of the gravitational potential. So the reason why this is the real Poisson equation is that this relation here holds at all scales, okay? While the 0, 0 component of Einstein's equation looks like the Poisson equation only on small scales, on sub-horizon scales, this relationship here holds at all scales. Very good. So the last thing I want to discuss for today is what's happening to vector modes and tensor modes. Sorry. So for vector modes, it's actually easier to start with the fluid equation. Okay, so our fluid equation for momentum fluctuations, you have the usual dilution of momentum, right? And the interesting part is that this is coupled to gradients of anisotropic stresses. Okay? Now, Einstein's equations tell us that this is equal to EI minus 2BI equal minus 16 pi g a squared delta qi. And these two equations together tell you why we never care about vector modes. Okay? So that's the first good result of the day. We are going to ignore vector modes hereafter. Why? Because you see here, momentum decays like a to the minus 4, okay, in absence of sources, but momentum fluctuations are only sourced by anisotropic stress fluctuations, okay? And for perfect fluids, those are 0, right? So for every standard thing, okay, you can't really source vector momentum fluctuations. And then the problem is that these guys are the source for metric fluctuations, for vector metric fluctuations, which means if this is 0, this decays, this doesn't exist, okay? So that's basically the argument for why we typically ignore vector modes. Very good. What happens to tensor modes? Okay, so for tensor modes, we only have one equation. And again, you see, as we discussed, basically, as we discussed, as soon as we have written down the scalar vector tensor decomposition, tensor modes are tensor metric fluctuations are only coupled to tensor anisotropic stress fluctuations. So again, for perfect fluids, these die out. Okay. Now, but you see here a nice difference with respect to vector modes. Okay. So with respect to vector modes, even when this goes to 0, okay, so we have no source, what happens, do a Fourier transform, okay, so this is k squared. So when we are above the horizon, okay, above the horizon, this term goes away, this we assume is 0. So above the horizon, I'm only left with these two terms equal to 0. A solution of this equation is h constant, okay? So tensor modes, differently with respect to vector modes that always decay, right? Tensor modes above the horizon are constant, okay? Now below the horizon, right? So when I restore this, and this is always also equal to 0, okay? So below the horizon, this equation looks like a damped harmonic oscillator, right? So you get a decay mode, something that decays in amplitude, okay? And this is the reason why these are hard to measure, okay? So these are cosmological gravitational waves. Now, people may try to detect these, right? Especially there's few proposals to try to detect these on with tabletop experiments, right? Um, the reason being that at tabletop length scales, right? So basically at the meter length scale, you don't really have astrophysical processes generating gravitational waves. So those could in principle only come from the early universe, right? What's the problem is that, if you generate these in the early universe, then, and these are very small scales, they had a long time to decay, okay? So their amplitude is very small. On the other hand, above the horizon, these are constant, which means that if you produce tensor modes in the early universe, then at least at very large scales, those remain intact. And this is basically the strategy that people have to try to detect these, okay? Basically to see their signature at horizon crossing. We'll get back to this in the next lectures. So we are done for the day. This was the most technical lecture. We needed to lay down our vocabulary to discuss fluctuations. Tomorrow we are going to see solutions to these equations that will describe fluctuations in cosmic structures, and in the day after that, and then on Thursday, we're going to see how we are going to use these same equations to describe the fluctuations in the cosmic microwave background. Okay? Very good. See you tomorrow.